Solve this question. You can see the question here. This is the picture. So a garden hose, it is attached with the nozzle, and we're using this nozzle to fill this bucket. Okay, so we're putting the water by using this nozzle here. So what we know from this problem is the inner diameter of the hose is 2 centimeter, and it is 8 centimeter at the nozzle exit. So you know the structure of the nozzle and how it works. So initially, so the inner diameter, it was 2 centimeter, and it reduces to 0.8 centimeter at the exit of the nozzle. Okay, so then the question is, if it takes 50 seconds to fill the bucket with water, we know initially the volume, it is 40 liter. Okay, so it takes 50 seconds to fill this bucket. That means the 40 liter of water. Right, we need to determine what is the volume and the mass flow rate of the water through the hose and the average velocity of the water at the nozzle exit. So here in this question, we need to fill the bucket. We need to fill water bucket, and we need to use the hose, and we are going to calculate the volume and mass flow rate and the average velocity. Right, so in this case we can write down some assumptions, like we can say that the water is a nearly incompressible substance, and no waste of water by splashing, so that we can say this is a steady flow process. So I'm not writing it here, as the substance is water, so we can write down the properties. That means the density of the water, it is 1000 kg per meter cube. Right, so once we know that, we will now start analyzing this question. So the first part was, we need to calculate the volume flow rate. Right, so in this question we have to discharge this 40 liter water in 50 seconds, and while we know the volume flow rate, so from the theories we already know volume flow rate. We usually define the volume flow rate is V dot, like this. It is the change of the volume in general sense and with respect to time. So what is the initially the bucket, it was empty, and the final volume is, let's say this is 40 liter. Initially it was 0, and it takes 50 seconds, so we can get it is 0.8 liter per second. So this is liter and this is the second. So the volume flow rate we got 0.8 liter per second. What will be the mass flow rate? The mass flow rate, this is so easy. We know mass flow rate, it is equal the density into the volume flow rate. So here we know the density is 1000 kg per meter cube. So we know the conversion unit, so we can write it is actually equal to 1 kg per liter. So we can write, okay, it's equal, and why I did it then I will show you later on. So you look here, the density we can say, okay, it's 1 kg per liter, and the volume flow rate is 0.8 liter per second. Okay, so then you can just cancel out this, and it will be, you see, the same 0.8 kg per second. So that's the mass flow rate. So the only thing is we got, you see, the difference of the units, it is kg per second. So that's the first part of this problem. Now we need to do some calculations for the second part, like we need the average velocity of the water at the nozzle exit. So the nozzle exit, the diameter reduces, and that's the usual thing. So what we can write down here for part B of this problem, we actually need the average velocity, right? The average velocity. So if I write it down like this, the average velocity BE, it is actually the volume flow rate over the cross-sectional area. So if we divide the volume flow rate by the cross-sectional area, then we'll get the, or we need it at the exit, so we actually need to divide by using the exit, the area at the exit of the nozzle. Okay, so we need the velocity, at the nozzle exit, so we can say this is the exit velocity. So the exit velocity. So what we need, guys, we already know the volume flow rate, but we don't know the cross-sectional area at the exit of the nozzle. So we can write the cross-sectional area at the nozzle exit. So it is kind of, the nozzle, the shape. So it's like phi r square. It's kind of a circular thing. So it's kind of, small circular thing. So it will be RE, as we are talking about the cross-sectional area at the exit of the nozzle. So we said the radius at the exit. But in this problem, what do we know? We know the diameter. The exit diameter, it is 0.8 centimeter. So radius RE, it will be 0.8 over 2 centimeter. Just we need to divide by 2 because we're talking about the radius. So look, this is the phi, and the radius is 0. So it should be 0.4. So 0.4 centimeter square. We can convert it into meter, but let's say I'll do it here. Okay, so we can write it as 0.5027 centimeter square. So this is 0.5027 into 10 to the power minus 4 meter square. So we got the exit area. So this is the exit area, and now we'll substitute the value here. So let's do it. BE, this is equal V dot and AE. So the volume flow rate is 80 liter per second, and this is 0.5027 into 10 to the power minus 4 meter square. So it is liter per second here, and it is meter square. So I can just convert it into like 1 meter cube equal 1000 liter. We're just converting the units. So then we can cancel out this liter, the meter squared, it will be meter, and this second will go down. So it will be kind of 15.9 meter per second. That means we got the exit velocity is this. So we'll show during the lecture that, okay, the average velocity in the hose, it was kind of 2.5, and the exit velocity we got 15.9. So it's increased, about 5 to 6 times, and that actually how the nozzle works. Okay, so that's all, and we'll discuss it during the